Hello! Today we are taking the equation that we had from last time and we are writing some Python prototype from it. So just as a reminder, here is our page from last time, and we calculated the coefficient for the frequency component. Alright, so the first step that we would like to do is we need an audio file to analyze. Lucky for us, I already made an audio file. It is of a violin playing. So let's preview the file. Alright, I think that's enough. So basically from about 2.5 seconds to about 3 seconds in the clip is where the first note is being played, and it is being held a little bit longer. So we will go ahead and use FFmpeg to extract just that bit of audio. Alright, we have extracted the note. It is just half a second of a note. Now that we've launched Spider, we can continue to code this. The first item that we need to do is we need to import the packages that we are going to use. So here we're seeing PyDub we will use to read the sound file. We need to import numpy so that we can do math. Import matplotlib.pyplot as pp. This will allow us to plot things. And the final item to import is OS. The other first item that we should take care of is we need to find the equation, and we can find this online, we don't have to derive it, of how to convert a piano key to a frequency. The other item that we are going to do is note how there is a MIDI note number here and a piano key number here. The piano keys start with 1, the MIDI notes start with 12, and actually for us it makes sense to use the MIDI note numbers instead of the piano keys, so we'll use those. The difference between them is 20. So if we take the MIDI note number minus 20, that gives us the piano key number. Now when we go to the equation, we will also need to modify the equation a little bit. The equation that we need is this one right here. We can also use this one. We will actually use this one because it is a little bit easier to use. But instead of 49, we will use 69 because we are working with MIDI note numbers. We define a function . So this Python function here, it takes a MIDI note number, which doesn't have to be an integer, it can be a floating point number, and it converts it to a frequency in hertz. In programming, we often like to leave comments, which this is obvious what it does, but we'll leave a comment anyway. Convert. So the next item that we will do is we will load the audio. So this first line, this PyDub is the package we are using, audio segment is class inside of it, and from file is a function that we can use to load a music file. Seg.getArray of samples will return us an array of samples, well duh, right? And numpy.array will make it into a numpy array so that we can do math on it. This next line will take samples and it will reshape it because numpy arrays have a shape. So it will make it into, because the number of channels, for instance, if it's mono, the number of channels is 1. If it's stereo, the number of channels is 2. So we just reshape it so that we can work with it more easily, because otherwise it is a flat array of just left sample 1, right sample 1, left sample 2, right sample 2, and so on. Whereas if we reshape it, we can work with just the left channel separately, the right channel separately. So that's what we do. The frame rate is self-explanatory, so this would be like 44,100, for instance, for 44.1 kilohertz. Let us just run this to make sure that it runs, and then we can probe what these things are. Samples.shape gives us the shape, so we have 24,000 samples, and the number of channels is 1, so it's a mono file. And so we can do operations on this. So the note list, we use numpy.arange. It creates an array with the first one in there is the 24 in this case, and then the last one is just before 108, and the step size is 0.1. We can convert this note list to a frequency list. So we can see that the first frequency in this frequency list is 32.7 Hertz. And if we look at the Wikipedia page, this contractive C is 32.7 something Hertz. So we know that our function here, note to freq, is working correctly. It is giving us the frequencies of the notes. And the last element is 4.1, 4.2 kilohertz. So here we created an array of the timestamps that we're going to work with. The timestamps are just useful for constructing this equation right here, because the sum is over t, so we need to sum over all the times. And actually last time we forgot to multiply this by time, so I apologize for that. There is a t that I was missing from the last video, but that is okay. As long as we remember it before we implement it. We would have been reminded anyway when the code wouldn't work. Alright, so we need an exponent. We can use numpy.exp for that. So this equation here is mostly right. This is the shift factor that we were working with. So just as a reminder, this is what we're looking at. Over here, this exponent of minus I. Now, in Python, when you want to say I, you actually have to type j, which stands for imaginary numbers. But otherwise, the phase list, that's going to be this component right here, 2 pi frequency times time. So this is what we have in the Python, 2 pi frequency times time. Now, one more item is missing here, and that is, in order for this to broadcast correctly with numpy, we need to reshape these. So right now, if we run this of course won't work because we have a certain number of frequencies and then we have a different number of times. So of course we need to reshape things. So freqlist.shape, this is 840. Let's just say we will reshape this to, so freqlist.reshape, if we can spell this correctly, reshape. Let's do -1, 1. So what this does is the -1 will tell numpy to reshape the 840 to this one right here. And then once we have the t's, we need to also do t's.reshape to 1 -1. So this will put, in this case, t's.shape was 4096, but it'll put it here so that it's the result here, the shift factor, is a two-dimensional array. So see, you have one dimension is for the frequency and the other dimension is for the time. So what we have here is we have taken the samples, and we will actually just take one channel of this. What we have here is Windows samples is an array of, in this case, 4096 samples from the audio file. Now we do have the shape of the shift factor, so we will need to broadcast the shift factor onto the samples, or I guess the samples onto the shift factor, because when we look at this equation, this is the s of t is the function that gives us the samples, and then this is the shift factor, so we need to multiply the samples by the shift factor. And then we need to do a sum of the entire thing over time, which will give us the coefficients. So let us do that. But before we even proceed with that, we need to make sure that this 4096 matches the dimension of the 4096 that goes with shift factor. So we do need to reshape this. So what that will do is it will take the 4096 and it'll put it into this dimension so that we can broadcast it together with the shift factor. So I can show you, this is Windows samples.shape, that's 4096, and then the shift factor shape is 840 4096. And the product, of course, when we multiply these two together, numpy will broadcast them for us, and it'll create this 2D array that is the product. So when we look at this equation again, we've multiplied this, so this is the product. Now we just need to sum over the time dimension. So what we've done now is we had the product, and then here we called the sum function, which did the sum for us. It added up all the axis equals 1 tells us to use this axis. So the time axis, like not the 840 axis, but the 4096 axis. And therefore the result is 840 long, so we have one coefficient for each frequency that we've input. Alright, so now what we have is we have a plot, but this is not quite what we want yet, because we are plotting, first of all, freq coef is a complex 128, which means that it has the real components and the imaginary components, but we don't even want that, we want the magnitude of this. Alright, so what we've done is we've changed to, instead of plotting freq coef, we're plotting freq pow. So this is the power, and if you remember, power is the intensity squared. So we calculate the intensity by taking the results, these coefficients, and we take the absolute value of it, which the absolute value is the value times the value conjugate. So that's what it gives us. Now, one other thing we should change about this is we are plotting this over frequency. We should be plotting this over note, because we want ultimately the piano note that this is. So instead of freq list, let's use note list. Alright, so this is plotted over piano notes. I can't quite see what that says. Let's actually make this, let's save fig. Alright, so that's better. This is better. Looks like I can't quite read these. Let's take the peak. So this tells us the index at which this spectrum is the peak. And then note list 588, that gives us 82.8, so about 83-ish. That's what it tells us. So the note number 83. So this is a B. Now this graph is very coarse. It does not tell us, it is very noisy. So to reduce the noise a little bit, let's go ahead and actually increase the window size. So instead of 40, 80, 40, 96, we'll do, let's try that first. Ah, that is much, much better. Okay, so, and this is the old graph. So we increased the number of time samples that we're averaging over, and that has reduced our noise dramatically. And do also keep in mind that just because this is the highest peak does not mean that this is the note that's being played. To tell what note is being played, we need to find the fundamental frequency, because a lot of these are harmonics, and sometimes the harmonic is louder than the fundamental frequency itself. So what we would need to do is, this might be, or this actually might be, this little bump might be the fundamental frequency for us, and that's just all we have to work with. And this is the signature of this instrument. These are the harmonics that it has. So we'll continue working with this next time, but basically, just as a review, what we did was, first of all, we started with this equation where the coefficient that we derived last time, the coefficients for the frequency components, and then we moved on to this Python script. We imported a package that can read an mp3 file for us. We imported numpy, which does math for us. We imported a plotting module, and we ended up not using OS. I thought we were going to use it, but anyway, we'll use it someday. But then what we did next was we found the piano key frequency chart on just the internet. Very readily available. We don't have to derive anything. Very nice. We wrote it up as a Python function, and instead of 49 here, as the Wikipedia page said, we used 69, just in order to be using the MIDI note numbers instead of the piano key numbers, to be a little bit more universal with how we do music. And then we loaded the audio file, we took the samples from it, we reshaped the samples to the shape we want, found the frame rate, and then we did some more setup. So the note list, we initialized just some range of MIDI notes that we wanted to look at. We calculated the frequencies from that. We reshaped that to the shape that we need to broadcast it. Then we calculated a delta t, which is 1 over the sample rate. This is useful for calculating the list of timestamps to be using for this. And the timestamps are useful for calculating the shift factor. So the t's, we reshaped that as well. The phase list is the phases that we use for the factor that we're using for shifting, and a shift factor is just e to the I to the minus I times phase. So we did that. Window samples is just the window of samples of audio, and then we reshape that. This is just a set of, this is in our case like 8,000 samples of audio in this case, what we ended up using here. And then finally we calculate the product, which is the inside the sum, what we're going to sum over. Then we calculate the sum. This is from the equation that we did last time. And then to calculate the power, first we calculate the intensity, which is the amplitude, not the amplitude, the absolute value. And then we square that to take the power. And then finally we use this code to make a plot of it. And now we have this beautiful plot. Yeah, so next time we can use this plot to do more interesting things with it. But for today, I'm glad we made it this far, and I'm glad we have a plot like this, and I hope to see you again next time. Thank you so much for tuning in.